Hi everybody, it's Brian. I want to today go over the new feature I've been working on feverishly in the last 3 weeks on StatPowers time series analysis, which is the design for the site has always been a suite of statistical tools that will be useful for someone in an introductory stats course. And time series is usually not in introductory stats. And just adding logistic regression was a new thing because typically introductory stats doesn't even cover logistic regression. But because I'm actually teaching introductory stats and I'm including a topic on time series because we have the time for it. So I wanted to create something useful in StatPowers that we can do some I'll say rudimentary and maybe I don't know even intermediate, but I'm going to say rudimentary time series analysis. So let's put in some data, time series data. I'm pasting it in, but I leave out the 49th row. So we've got is your data entry is going to be straightforward. It's just rows of numbers. Everything's going to be put onto individual rows when you paste it in. Whether you label the variable or not is up to you. This is actually cheese production. So let's look at what we can do with this. First of all, the most basic thing you'll want to do with time series data, and actually I'm going to hide that and just look at a time series plot. Actually, now that I realize it, I have to click calculate now to just get things going. Okay, my time series plot is a line graph, and we've got a bunch of all of the values of my data in time order, and you have a couple of choices. You can either connect the points or not. If you wanted to have the points connected, of course, you could download the chart. The one thing that people like to do is to smooth out your jittery time plot by adding some sort of smoothing function, smoothing model. So there's a few down here. You can click add a model to add a, let's say a cumulative moving average. It's now this doesn't look that great because what a cumulative moving average does, it averages out your data as time goes on, so that over time what you have is, so at time period 1 it's the average of the first time period. For time period 2 it's the average of the first and second time period. For time period 3 it's the average of the first 3 numbers, and so forth. By the time you get to the end, it's just the average of all of your data. A cumulative moving average often, if you have a trend, is usually not going to be a very good model. So maybe a moving average which is like, say, the last 4 values averaged together. That's a span 4. You can change the span 4, 5, 6, 7. The more you increase that, the smoother it's going to get, but also it doesn't start averaging. Now a span of 13 doesn't start averaging until you get to the 13th time period. A centered moving average is going to fit the data points a little bit better, but of course you can't use a centered moving average as a forecasting method. Like you can't use, what it can do is after the fact you can take the last 5 data points and smooth out, get a smooth a moving average where it's centered at the point. But anyway, there's a couple. I mean, you can add. There's a couple others that are in the literature. A Hanning filter, which is it weights the average between the last between the point you're at and it's like a centered moving average where the weights are, it's higher on the middle and a little bit less on the sides. In fact, it's 25%, 50%, 25%. You can add multiple smoothing models. So I could put my moving average, my centered moving average with a span of, let's say, 5 in blue, and in red have the Hanning filter. So you can have multiple, you can remove them if you don't want them anymore. All right, now one thing you can do is, okay, so the stationary test is a test of whether or not your time series is stationary. Now, a stationary time series has the mean and the variance doesn't change over time. Now, this one has a trend, so it definitely is not stationary, because if you look at like the first half of the data and the second half of the data, the mean is totally different, right? Maybe it has the same amount of variation or not, I don't know, but it definitely isn't stationary from a mean standpoint. Anyway, the stationary test it's a Dickey-Fuller test, and you can set the significance level, and you can choose one of three types of tests to test. The first model is to not test with a constant or a trend. The second is with a constant and no trend, and the third is with a constant and a trend. Depends on how. For this data, because we have, I would probably say constant and trend. I want to see if it detects that it's not stationary, and it says. So the null hypothesis is that it's not a stationary time series, and the alternative is that it is stationary. The conclusion it's going to give me is to fail to reject the null hypothesis. It used the Dickey-Fuller test. It's a little bit complicated. Roughly speaking, it calculates a tau statistic, which is like a t statistic for simple linear regression, but it's a little different. And it gives you a tau statistic and a tau critical value. And if the tau is lower than the tau critical value, then it will it'll reject, and you'll have the Dickey-Fuller test would tell you that it's stationary. Now, when your time series is not stationary, you can apply transformations to the data to make it stationary. Essentially, you can look at whether the residuals are stationary if you do a simple transformation. So let's look at open transformations and add a transformation. This one definitely looks like it has a linear trend. So what I'm going to add is a linear trend transformation. I can specify the intercept and the slope anything I want, or I can click autofit to do autofit a simple linear model to the data, which is the simplest thing to do. What it's going to do is, since I've already have click plot residuals selected, the residuals are going to be shown. Now, the residuals are the original data points if I have no transformation. Checking that or unchecking it doesn't change things. But if I click plot residuals and I autofit, you're going to see this change completely. Okay, so now I have things zigging and zagging, but it stays pretty level. Now I could see that it zigs and zags less in some places and more in other places. We can see whether the variance is changing and see the results of the stationary test. And it looks like for the constant and no trend, the conclusion, if you're looking at the simplest model of a stationary test, it says that's stationary if it's just no constant, no trend. But it looks like if you have a more complicated model, it still thinks you're not stationary. If you wanted to see what the line of best fit looks like with your data, unclick plot residuals, and you'll see the dotted line of the line of best fit, and along with your data points. Okay. So there's another kind of you can stack on transformations if you want to. I'm going to keep my residuals shown, and I'm going to add on another transformation. Let's see, something that might be useful. I'm going to let's remove this transformation that I did and back to my original data, and I'm going to add a different transformation, and this one is the difference. And what it's going to give me, my residuals are going to be the difference between each point and the next point. And we can see whether the differences are stationary. And this is a very different looking thing. Now the difference from one point to the next zigs and zags and zigs and zags. So the idea is that if you can model the differences using some time series model, then if you have a starting point, you can sort of let your time series go, and then you can And then you have your you can kind of make forecasts of the future. Here, the Dickey-Fuller test looks like it does think that my differences are stationary. See, going the first, second, or third model, it always says reject the null hypothesis, which means the time series is stationary. Oftentimes the differences are going to be stationary. Another thing that you can use to kind of assess whether it's stationary or not, is look at the autocorrelation function. And the autocorrelation function for a stationary time series, the autocorrelation tells you at each, like, the lag is a difference between two time periods. So a lag of 1 is like the difference between now and one time step from now. And this is the autocorrelation function tells you for two values that are separated by one time step, how correlated are they? For values that are separated by two time steps, how correlated are they? And so forth and so forth. And the red dotted lines are going to give you sort of tolerant bounds where the correlation is very, very low. It's considered low enough that it's not significant. There's some autocorrelation function charts include 0, which is kind of silly because you always have an autocorrelation of 1 for a zeroed lag, because how correlated is data with itself? It's perfectly correlated. It always has a correlation of 1. So it always is 1 but then it's going to be low. Differences, so if I go and I remove the difference transformation, I can look and see, now this is my autocorrelation function with the differences not there. You can see that each time step is very highly correlated with the times that came before it. I can look at, if I added back that linear transformation, that linear trend, we still have a pretty high correlation with the values that came before them. And so that just adding a linear trend doesn't account for all of the correlation in our like the autocorrelation, but the differences did. There's also this part. Let's add that difference transformation back. I know I'm jumping around, so I hope you forgive me. The other one is a partial autocorrelation function, which is it's going to roughly speaking, it tells you how correlated each value is, the time lag, taking into account the other time lags, and it's gonna oftentimes look similar to the autocorrelation function. It depends on the data. I guess you'll read more about the partial autocorrelation function. I guess what I want to show you is a different. I'm going to show you a different data set, and we'll look at some other kind of features of StatPowers. Okay, so what we have here, I pasted in some CO2 levels, and I'm going to click Calculate Now. I'll label the variable CO2. Now the time series plot is going to show a very, very obvious sort of cyclical pattern. And if I were to look at the autocorrelation function, you'll see this autocorrelation function has this same kind of wavy pattern. So it looks like the data points at time series at a 12-step lag and a 24-step lag and a 36-step lag are the most highly correlated, which means that this is monthly data. So every 12 months there's sort of this cycle that continues, which I can try to account for in a number of ways. The first thing I want to do is I have this linear trend I want to account for. So I'm going to add a linear trend transformation, and that's going to take care of the linear trend. The next thing I want to do is I want to add another type of transformation, which is a sine wave transformation. Now the sine wave is going to have I want to set the period of this sine wave to be, well, it's already set at 12, which is the period of this this loop. Now I want to also set the offset to be 4, because if you look down at the autocorrelation, it's like every four time steps, the correlation is 0 again. That's actually that's where the sine wave would be 0. So I'm going to set this at 4, and modify my amplitude now. The amplitude, I want to move the amplitude up a little bit until I am able to, let's see if this takes care of a lot of this. It doesn't fully take care of my my correlation problems. Let's see. You could see that like we still have a lot of autocorrelation every 12 time steps. Even that, if I'm plotting if I was just trying to get the dotted line of this fit to match nicely, you can see how changing the amplitude has an effect here. Okay, so it looks like an amplitude of 3.5, 3.3 looks pretty good. However, that's not going to take care of all of my autocorrelation. There's still a lot of autocorrelation. And let's take a look at the time series plot. I want to look at I'm going to look at the partial autocorrelation function for here. Now the partial autocorrelation function is a good indicator of how many time steps of like in the past can sort of predict where we're going to be. You looking at the partial autocorrelation, you can see that one time step of lag tells you a lot about where we're going to be. And so there's a model that's useful for that, which is the autoregressive model with autoregressive 1, which is to say, if we're like the prediction of where we're going to be at each time step is going to be based on it's going to be a constant and then a scalar times where we were one time step ago. It's like a simple linear regression where the y value is the time series data, and the x, the predictor, is the one lag removed. And so what we're going to get is, you can see this red line it kind of follows along this. The red line is an AR1 model, which means to predict each value, it just takes the last prediction. I'm sorry. It's a constant value plus some scalar that's calculated by linear regression times the previous time steps value. Now this looks like it looks kind of like it's just a some sort of, it's like just a lagged prediction. I'm going to compare that to a moving average with like just a span of 2. It looks like, I mean, you can see sort of just like lags one step behind. I don't know how good that really is, but we might find that an AR1 model is much better at giving you at predicting differences. Let's see. But looks like the the differences are not doesn't look like an autoregressive model is a very good fit for the differences, because there's really no they're not partially autocorrelated with each other, really. Yeah, autocorrelation, the differences are really just noise. It seems like it's just random stuff with a mean. And you can see actually if the differences are stationary. It looks like the differences are stationary. Like it's a stationary time series. The difference is one step to the next. So what does this all tell us? You know, for the Dow Jones, it seems like, although it looks like it makes this pattern, it seems like it's just a sum of all these random differences over time, which are not correlated with each other significantly. So, yeah, you know, I guess the main thing I wanted to show is just all of these different little features that StatPowers has. I think there's, aside from transformations, there's summary statistics. Now, actually, one thing you can see with summary statistics is you can actually look at the transformed data, which is like you can look at the mean and the standard deviation and stuff of the transformations, or you can look at the original data's mean, standard deviation, so forth and so forth, which is handy. And let's see, you got your charts, you've got adding models. Let's talk about another smoothing model. Let's look at our plot, and I'm going to remove that transformation. Okay, and I'm going to actually not connect the points either. Let's look at another type of smoothing we can do, which is the exponential smoothing. And exponential smoothing is handled by there's a couple different features here. So the lambda is a parameter that says how much should the smoothing be based on the new value of the time series versus what the previous smoothed value was. If you set lambda all the way down to 0, it's going to say, well, I'm just going to take the previous smoothed value, and it's going to be like that every single time. If you set lambda all the way up to 1, it's just going to connect the points. The smoothed value is going to be just each day's value with 100% weight and 0% weight times the previous smooth day's value. So somewhere in the middle, you end up getting in 0.2, 0.3, something like that. A lot of times, this is going to show you the trend. It's the smooth trend without having too much of the noise of the ups and downs. There's other kinds. So if you're looking at this exponential smoothing, you can either look at it, treat it as a forecast, like looking at tomorrow's value or today's. And all it's going to do is going to bump things forward one notch. There's also second order exponential smoothing. I think we can do first and second order. Second order, when you have really big trend dips, a second order exponential smoothing often is able to smooth those, kind of follow those dips better. For example, I'm going to clear my data and show you a different data set that has a really big trend. Okay, this is CPI data, the Consumer Price Index. And let's look at this time series plot. There's a really, really obvious trend. It's a very linear trend. And if I was to try to smooth this with a exponential smoothing curve, it looks like I'm really kind of a little slow. I'm not going through these points very well. But if I do a second order, it captures this trend way better. You can see the red. I'm gonna not connect the points so you can see a little bit better. Yeah, you can see how I'm hitting I'm going through the midst of these a lot better with this smooth curve. We can adjust how the lambda on this, it's pretty good just with a lambda of 0.2. So anyhow, and actually it might be curious to see how well, if we take care of the linear trend, what the results. So you can see how things are a little bit. The reason it's wacky is my initial value has to be set to be. I think I want the initial value to be closer to 0. One thing I need to fix is the scaling, the y scaling not changing when you are choosing whether to plot the residuals or not. So you can see that this is pretty good capture of the residual off of this every time, but and actually the forecast I think is going to be fine. Now, actually, one thing I didn't talk about is for any of these models that you create, it's giving you a bunch of metrics that kind of tell you how good of a model it is, and these are abbreviations that are commonly. I'll tell you. We'll just go through one by one. And this isn't really an instructional video on time series, but more of showing the features of StatPowers, but still, we'll talk about each one. So first is ME, that's the mean error. So that takes the difference between each predicted value and the actual value, that's the error, and just averages all of those errors. If the mean error is 0, that means your forecast is unbiased. So the average the difference between your average prediction and the average value would be the bias of this model. So if you want an unbiased model, you want your mean error to be 0. The mean absolute difference is instead of averaging the errors, you average the absolute value of the errors, and so. Because if you have a positive error and a negative error and a positive error and a negative error, they kind of cancel each other out if you're just doing mean error. But if you make them absolute value first, and you average out all the absolute value errors, well, you're going to be counting all of your errors, and so if you want your MAD to be close to 0, then that's looking at a very accurate kind of forecast. The mean squared error is the mean squared error is you square all the errors. So MSE, square all the errors and you average those out. The root mean square error is you it's the square root of the mean square error. All 4 of these metrics are all in the units that you're working in, and they're also going to be So it's in the units and scale of the data that we're working with. Now I've applied a linear trend, but if I want to take off, if I wanted to say, well, what's the how far off am I like percentage wise? If I was like if my mean square error was really low, but that means that I'm like 200% off in value, that's a big problem, right? Well, okay, this is the mean percentage error and the mean absolute percentage error. So these values these metrics are not going to really make sense if my data is close to 0, right? Because if my data is close to 0 and I'm off by a tiny amount, that can be a huge percentage error. Because I've applied linear trend, this is looking at the errors on my residuals, which is more problematic. Let's see if I change that. Now, if instead of looking at the residuals, if I uncheck that, let's change my initial value back to 150. Here, I have changed things to this is looking at the model on the original data, and what I've done here is I still have this linear trend transformation, but I've backed out the linear trend. And what I have now The mean error 0.397. That's in computer consumer price index units. Mean absolute difference is 0.57. The mean squared error is 0.513. But so this mean percentage error, that's 0.235. That means on average, my forecasts are about 0.235% off. A little bit higher than it should be. So I do have a bias. If I and then my mean absolute percentage error 0.333, which is this is in percentage, so it's 0.333% off on average, which is pretty low considering these are forecasts based on the past. So at any rate, so when you add additional models, as you add them, let's put an AR1 model in here and just see. I think if I can look and see, I think it might not be showing me the AR1 model just because the something is up. I'm going to, if I'm doing that, it's going to show it off of the residuals. My point that I wanted to talk about is if you've got two different models, you can compare these metrics between the two models and see like, oh look, the AR1 model has a lower mean error, it has a lower mean absolute difference, it has a lower mean square error, it has a lower root mean square error, but of course because we're looking at residuals, the mean percentage error and the mean absolute percentage error are way higher. If I wasn't looking at residuals, you can see it's actually it's not backing into the original correctly. So there's a problem there. I have to do a little bit of tweaking on some of this stuff. If something looks totally off, then there's probably a little bug. This is all very new, so if there's bugs, I apologize. But it does give you some tools that you can play with some time series data, play with transformations, look at how autocorrelation is affected, and so forth. So anyway, I hope that you got something out of this, and you're feeling more comfortable kind of getting your hands dirty with some time series data with these very easy to use, though not necessarily always easy to understand tools. Hopefully it makes things a little easier to understand. Anyway, this is just the beginning of your journey in understanding time series. There's a lot to this science, but this is just to give you a bit of an introduction. So I'll leave it at that. Thank you for watching. Take care. Bye.